Good morning, class. I hope everybody's doing okay. Again, we're enjoying some warmer weather. It was actually nice to go to rehearsal last evening, and it was very comfortable. I guess we're going to have another warm summer, but I guess I've become accustomed to that. And when I have to think of the alternative of having very severe winters, I'm happy with the warmer weather. So I hope that's uh, good for everybody else. What we want to do today is to complete some examples that we have in the end of the section on geometric. That's a really important section. And of course, it will be covered on the final. But like I said before, what we've been doing lately has been more focused on algebraic constructs that you saw previous to the trigonometry. And so we're kind of coming back, toggling back and forth between the two disciplines, so to speak. But I want to cover some of those ideas. And then let me remind you that now the test is available. You will have the window of today and tomorrow to complete. And I probably will send another reminder just to kind of keep everybody in the schedule mode. Remember that you will complete the test and then scan your work as you normally do, scan to make one file and then upload that to Blackboard. That is an essential task. And most of you by now are doing that very well. I recall last semester, and I thought it was very interesting. I had one student who always wrote his test work using his Wacom tablet. And of course, he had it down to a fine art science, and he'd use different colors and all the terminology from lecture, and it was amazing. And the student told me from the very beginning, he says, Professor Ron, I want to be a computer scientist. I said, well, good. Your meticulous approach to math will certainly pay off. So you have complete flexibility. A lot of you do your work on paper like I do. You have many modes that you can access. So however you want to present your file is completely up to you. You have complete control over that. And other students, again, they had their signatures that they used. So I appreciate that. And that again, just gives you the opportunity to put your best foot forward, for you to present something that you would show to any of your colleagues. So again, I appreciate your attention to that, and I wish you well as you continue to prepare. Now, what I want to do is share the screen and go to the problem that we were working on at the end of last lecture. Now, if you recall, and I think I actually wrote on the actual paper, so I don't want to just spill the beans. So let me go ahead and draw what we had as just a little algorithm to give us some way to approach this problem. Remember what I had drawn, we had a bouncing ball, so to speak, and we had a distance of 9 feet. That is, the ball is dropped, and then it's just going to bounce up 1/3 the distance it has fallen. And so we wanted to do this 5 times. We're going to have the first instance, the fourth, well, the first, the second, the third, the fourth, and then the fifth. So, again, not Rembrandt, but good enough. So this is the first instant that the ball strikes the ground, the second, third, fourth, and fifth. Now, when you think about this and you think about what we've been doing, so I'll just say ball bounces up 1/3 distance traveled. So this is going to, like we said before, generate a geometric progression. Now, you can think that the next problem or the next part of this question will be, well, for instance, what is the distance traveled on the instant of the nth strike? For instance, when we have that opportunity to generalize, we're thinking, well, what if we're doing a problem where we're solving certain types of equations and it keeps repeating over and over with different inputs, but it's the same problem. So we're thinking, maybe we want to generalize this. So there are two ways to actually do this. We can be very careful about how we set up our arithmetic to basically input the parameters, and then the generalization is easy. So let's just kind of look at this and say, well, when we've got this situation here, we've got some numbers that are really important. This 1/3 we're thinking of as a common ratio. And then we've got this 5, which will eventually be generalized to maybe n, the nth strike, or the instant of the nth strike. So we've got that, and we've got this 9 over here, which again may get adjusted depending on how the arithmetic evolves. So we're thinking that these numbers are kind of principal as parameters. And then of course, if we wanted to, we could consider this to be 1 and generalize that. So what we want to do first is just say distance here. I'll just write it as distance. We won't give any more variables right now. So when we start, we go 9. That is, the ball will fall a distance of 9 feet or 9 meters. I don't really care about the units at this point. You can be 9 inches, it doesn't matter. So, and as I wrote before, here I'll use blue here, we've got to consider the up and the down part, which will just be replicated. So I remember drawing something like this. So when we look at the distance here, that is, the ball will travel up 1/3 the distance it just previously traveled here, but up and down. So that's a factor of 2. So we get 2 times 1/3 times 9. Again, up, down, the same distance. Now, as we move again, we're gonna start getting the same thing. That is, now this is the previous distance that the ball fell, and we're gonna take 1/3 of that. So we're gonna have 2 times, and of course we can just do 1/3 times 1/3 and might write it as 1/3 squared. So if you like, you can just kind of, say, okay, that's this part, that's this part. And then when we get to here, again, we're going to go up 1/3 this distance. So 2 copies of it, 1/3 cubed times 9 for this part. And then for the very last part, same thing. Again, the ball will bounce up 1/3 the distance it has previously fallen. So this will be 2 times 1/3 to the 4th times 9. So to make this a little bit more systematic, we can just say 1/3 of the previous distance and use our laws of exponents. And that way we can, at least in the first level of analysis, we can see the generation of the powers of the common ratio. Again, when you work physics problems and you work engineering problems, we're always looking for patterns, because we know if we're going to apply the mathematics, there's got to be a pattern that opens the door to some type of mathematics, be it an identity, be it a solution strategy for solving an equation. There are all kinds of things that we look for in mathematics, and they're all developed based on patterns. So now when we look at this, we're thinking, okay, this can be our first term, this can be our second term, our third term, etc. So let's think about it that way. And this term is kind of the rogue term. It's not really part of anything. So it's just hanging out. So we have 9. And now if we look at this and we think about it, notice here, we've got a 1/3 times a 9. And we look at that and say, okay, well, that's a 3 times a 2, which is a 6. So let's write that as our first element, our first term. And now as we move over here, if you like, and let me just kind of reinterpret this, we're going to have a 2, and then we have the 1/3 times 9 times 1/3, just kind of redistribute the numbers there. But notice now, again, here we have the 6 times the 1/3. So here we have 6, oh, nose itches, sorry, 1/3. So here, if you like, the 6 is just going to be that first element that repeats throughout. And then with the same idea here, we'll have 6 times the 1/3 squared. So we've got this, and then this one, and then this one, and then the very last one. Again, with each of these, we're always going to have the 2 times the 1/3 times 9, which is the 6, here times 1/3, here the 6 times 1/3 squared, and here the 6 times 1/3 to the third. So the key with all of this is trying to write a formula that showcases this 1/3. We keep thinking about this and saying this must be the common ratio that we're looking for. So if we take a little bit more time with this, generalizing will be easy. So now, again, this number is kind of the rogue element. It's just off to the side, but we certainly remember it because it's very important. But here we have the geometric progression or geometric partial sum. Now that is critical. Students, again, when they get to infinite series and sequences in Calculus 2, often suffer initially because they don't look for the patterns. You have to look for the patterns and then react to it. And now we're thinking, okay, can we write this in a way that compactifies everything as a sum? And we can easily do it. So this will be 9 plus, and so we have our summation notation. I thought about this and I said this would be the nicest way to basically interject the theory that we talked about in the previous lecture and then make the problem a little bit more manageable. So now remember, this will give us n equals 1. In this case, to 4, because remember, we're going to have 6 times 1/3 to the n minus 1. So now when you look at this, this is exactly how we derive the partial sum. So we're just basically working backwards from that theory. We have, again, the a, we have the r to the n minus 1, n equal 1 to, in this case, the n. So you're thinking, you know, if we want to make this look really nifty, so we know that's an n, let's just go ahead and make this a k. That way it looks just like what we had before. Let's go ahead and make that a k. And that way we know that's the n right there. So let's just treat it just like we did at the previous lecture. You know, the notation is not so much an issue, but if it's consistent with what we did before, it makes it a little bit easier. So now this mimics this, but then we're good to go. Because now we can write down the actual formula for the partial sum. Let me go back up here and remind you that we derive this. That is k equals 1 to n a r k minus 1, and this equals a times 1 minus r to the n. That's why we need the n up top, and that way it's very clear what we mean, divided by 1 minus r. So this, and of course, when we have the infinite case, the r to the n goes away and it's even easier. And that's going to be a big plus when you do calculus too. So now we have this stabilized in our computation, so we can move right to this formula. So we have 9, again, remember the 9 is kind of the rogue element, plus, now we have a, which is 6, and then we have 1 minus 1/3. Now remember, let's see, where's the n? The n's right up top here, that's 4. Remember that bumped up 1, divided by 1 minus r, so 1 minus 1/3. So this is a direct application of the theory. Even though it's pretty simple, it's actually very important, because we found out last class, and you're going to say more about this in your calculus, that this exists in the infinite realm as long as the absolute value of r is less than 1. So this is a critical importance. So now let's clean this up and see what it looks like. So we have 9 plus 6. Now, of course, this will just be a 1 minus a 1/3, which is a 2/3. So upstairs, of course, we've got what? If we raise 3 to the 4th power, we just get 1 over 81 divided by 2/3. So just basic number theory from general math, right? So 9 plus, so now this will give us 6, of course, invert and multiply, times 3/2, 1 minus 1 over 81. Now, of course, the 2 will absorb into the 6 to give us a 3, and a 3, so this will give us a 9 clearly. Let me just write that up there. So this is 9 plus 9 times 1 minus 1 over 81. So, of course, there is nothing unique about what I'm doing. I mean, the computation here can be done as long as you're adhering to the partial sum. So again, my technique is based on the fact that I'm trying to work this in a way so that it will be very easy to generalize. Otherwise, if we're sloppy, then we've got to work a whole lot harder to get a generalized formula. And that's not what we want. So now you look at this and say, okay, well, it looks like we're going to get 2 copies of 9. So that's going to give us an 18. So now we're thinking, all right, if we wanted to generalize, this number here is going to be twice the distance that the ball initially fell. So that could be a generalization point if you like. And now, of course, here we have 9 times the negative 81. So this is minus 9 divided by 81. Now we've got these numbers up here that we need to find some way to fit into this. So this will be 18 minus, well, 9 over 81, that's 1/9, right? Okay, so now we're thinking, all right, well, that's 17 and 8/9. Okay, fine, that's an answer. That's the correct answer. Whatever, that is the answer that I asked you to compute. But now let's try to work these numbers in. So we're going to do that. And let me just write this on the next page. And then this is going to help us generalize since I'm running out of room here. So here we're thinking, all right, let's go ahead and reinterpret the 1/9 as a power of 1/3, which is easily done. So this gives us 18 minus 1/3, in this case, squared. Okay, so there's the you know, we look up here, so we've got this down, so I'll just go ahead and cover this up. We've got the 1/3, right? And now, what are we going to do with this? When we look at this particular example here and we think about what we need to do, it's like, how can we now get the 5 in? So note, this is, you might think this is kind of arbitrary. Observe, in this case, 2 is equal to 5 minus 3. So now we can say 18 minus 1/3, 5 minus 3. So now we have the R, and we have the 5th instant, and there's the 5. This is the 5th strike, so to speak. Okay. Now, when you look at this, you're thinking, okay, this is pretty generalized. And then, of course, if we wanted to write the 18, if we're going to give the initial height a special letter like D, we could call that 2D. But that's just another part of the issue. So if you want to generalize that, it appears that we could write this as 2D in the most general setting. So now we don't have to worry anymore. We now have a formula that encompasses the ratio, that is the common ratio 1/3, that is the ball bounces up 1/3 the distance it has fallen, and then we have the occurrence of the number of the strike, okay? This, the 5th instant, so to speak. So this implies we can now write a general formula, and we can say D, where N is the strike. First strike, second strike, third strike, fourth strike, millionth strike. But now, of course, this has a very nice algebra to it. So this will be what? 18 minus, now we've got the 1/3, which is the R. And then we have N minus 3. So we've generalized this, but now we could write, and I'm going to even write a more generalized formula after this. But if we wanted to write this, the question says, now write the distance traveled as a function of the nth strike. And you're like, oh, look at that, Professor Ron. So now when you look at this, you're thinking, okay, does this work? Well, of course, n greater than or equal to 1. So let's check it out. Well, of course, we know that D of 5 is that number, 17 and 8, 17 8/9 and 8/9. We know that, but let's just check it out. This is inductive now. This is something we can think about when we do mathematical induction next week. So D of 1 will be 18 minus 1/3, 1 minus 3, which is 18 minus 1/3 to the negative 2. But of course, that just reciprocates. So this is 18 minus 3 squared, which is 18 minus 9, which is 9. And that's clearly consistent with the distance that the ball has fallen at the instant of the first strike. And then, of course, we could just keep computing. So basically what we have here is an inductive formula where we are doing induction on the number of strikes. So this is why I'm doing this, because I'm trying to make a segue to our next lecture. We will investigate logical statements about natural numbers. And what that means, if we have the natural numbers, 1, 2, 3, 4, 5, etc., and we can come up with these logical statements that we would like to show are true for all natural numbers. That's called an inductive principle. And so we're thinking, all right, well, Professor Ron, what you did is kind of like an algebraic manifestation. You know, you're thinking, oh, I see what you did. You came up with the formula algebraically, and then if you wanted, you could test it by induction. So what you're seeing here is that I tried out 1, okay? I tested one and it worked. So I would say that my logical statement for n equal 1 is valid. And then later on, what I would want to do is say, if I take some arbitrary n, can I, and assume it's true for that n, can I show that it's true for the next or the successive natural number n plus 1 by making that assumption? And if I can do that, then I have proven the result by the inductive principle. So this is where students think, oh, I got you. If you give me a formula, I can verify it by induction. Otherwise, I can just kind of work around algebraically like we've done here. When we look at this, we're thinking, okay, we did the algebraic manipulation, and then you're thinking, oh, we come up with a formula. And then we're thinking, that's it, I don't need to do anymore. But what we think about is the induction as just being the last instance of verification. You're thinking, I think I've got a good formula here, so I'm going to just do a quick verification by induction. See if there are any problems with my algebra or whatever. So you're thinking, oh, our partial sum formulas are inductive. You know, the geometric progression, the arithmetic sum. You know, when we think about the arithmetic sum, we've got a D and we've got an N. And so we can think of that as being a type of inductive procedure. But definitely this right here is inductive because it's based on the number of elements in the progression. So I thought this was an excellent example to showcase how we can generalize just by being very fastidious in a more specific case. So now, if you're thinking you have a problem, we could say in general, let's do this. In general, we could say initial height. We'll just call the initial height D, okay? And we can say the common ratio is R, which we get in this case is 1/3. And then this would imply, in the more general case, say you wanted to generalize this problem, say you wanted to, the ball started at 20 feet instead of 9. And maybe you have it set up where the common ratio is 1/4 or whatever. Maybe you've got different parameters, okay, based on whatever type of model you've created. So you could say D of n equals, now we've got what? 2D minus R to the n minus 3. So this would be a more generalized setting right here. And that could be something you could prove by induction. But again, what I'm trying to focus on here is that this formula is not necessarily unique. You could work your algebra a different way and it maybe wouldn't look this way, but this is so simple. I mean, this is like, how simple can you get? And let me just reiterate, this is very important. When you start to realize that you have a geometric progression, what you want to do is to develop the pattern and then try to introduce the parameters of the problem. Okay. And otherwise you do this in a piecemeal fashion, you get a number, which is what, 7, well, let me just to make everybody happy, this is 17 and 8/9. Okay. So that really accomplishes this task. But then if we look more closely, we can now basically place the parameters of the problem on the formula and then get the easy generalization. So again, it's like this. You work all your problems for a physics class or a math class and you're a week ahead of the test. And you're like, well, I'm done. No, you're not done, because if you don't study in a week, when you take the test, you'll fail it because you will have lost all of your edge unless you put everything in long-term memory, but I doubt that would have been the case. So it's kind of like you go back and look at the problems and you rethink what would be a good way to work this problem and think about it a little bit differently. So that's why I like the homework problems that you have, because again, you have a specific instance here when you are trying to basically model the instant at which the ball strikes the ground as your variable n, and then generalizing. So again, I want you to take this problem as an inductive procedure. And then hopefully when we start talking next week about the principle of mathematical induction, this won't be so strange to you. So this is a classical problem and an excellent example of the geometric progression. So this can be manipulated. You can always re-index. I've shown you how to do that, but always have something on your note card that grounds you with the geometric progression, and then you're good to go. Now, there was an example that one of your classmates asked me to do. And this was another one on geometric that I want to do. This actually is a problem from your homework. And the student was like, I need some guidance. And I said, well, be sure to study the material on geometric. So we have a geometric sequence. And then there's a good example of a conic section that I want to do, which will be, good review for the test. If you can actually do the stuff we've been talking about with the progressions, the trigonometry will not be hard. I think by now you're seeing that the arithmetic of the unit circle is kind of the key, and the ratios of the sides of the triangles. So we've got a geometric sequence, and we're given that the third term is -50. And in this problem, this is directly from the problem that the student was doing. The sixth term, so the problem wasn't stated with the subscripts like I do, when I teach. It just said the third term is -50 and the sixth term is 3,125 divided by 256. Okay, that was the given right there. And then it says, here's what the problem asked the student to do. Compute first and second terms of the sequence. Obviously, it's the sequence, first and second terms of the infinite series. I'm just being silly here. So when you look at this, you're thinking, okay, this is kind of like the problem we did with the ball bouncing. We think it's probably going to be geometric, so we try to discover that, okay? Well, in this example, we're given that it's geometric. So we're like, thank you. But I think the student was a little bit taken aback because it seemed like there wasn't enough information. But trust me, there's plenty of information here, because what do we need for geometric? We need A and we need R. That completely defines the sequence. So first, we just recall that famous word, recall or observe. Recall that the general term, the nth term, is just A, R, n minus 1, just like when we were doing the partial sum formula. This is how we constructed the geometric sequence. That is, we start out, of course, with n greater than or equal to 1. So this is what defines the geometric sequence. So now you're thinking, I can use these numbers with the n to figure out, hopefully, A and R. So this implies, so we'll look at the -50. -50 is the third term, so we have A, R, and 3 minus 1, that's a 2, okay? So for the third term, this just says n equals 3. But we know the term, it's -50. And we have the sixth term, n equals 6. So we have 3,125. Of course, we'll do a little factor tree or do a division. I think you see we've got some nice numbers here. So the author was good to you all as students. So now, of course, we'll have what? A, R, and then we've got what? 6 minus 1, which is a 5. Okay, so when you look at this, you're thinking, oh, take ratios. The idea of taking ratios will allow us to solve for R, no pun intended, because the A will absorb, and then we can work backwards using either equation to solve for A. So when you've got this much information with the geometric progression or geometric sequence, you certainly can figure out the first and second terms, or any term of the sequence for that matter. So now at this point, and this I think is where the student just needed some help, and so take ratios. Of course, the idea is that when we, just like doing the last problem, you start looking at it and it's like, well, why would I know to do this? Well, we've got to set up the geometric progression. So in order to set it up, we've got to know what A is. We have to know what R is. I mean, when you think about it, ladies and gentlemen, all of this we have to do to get to a form that matches what we're interested in. Model to fit the theory of the geometric sequence. So now let's just do this. So this will be A R to the 5th divided by A R to the 2nd. Of course, the A's absorb, and that gives us R cubed, right? So that's nice. These absorb. And now we have 3,125 over 256, and we divide by negative 50. So we just say invert and multiply, negative 150. Okay, so just go ahead and invert and multiply. Now, of course, we're in good shape because we know 25 divides this. So, and of course, 25 divides that, and we're looking, this is looking really nice now. So of course, we'll say 25, and this is not hard to do. 25 into 31 will go one time. And then we have what? We've got a 62, so that'll be 2 times, so 62, and that'll leave us a 12, so a 125 divided by 25 is a 5. So that we can do like we're doing subtraction, or when I multiply and I make sure I've got plenty of zeros. So that's not difficult there. And then of course, remember we started doing this last time? 256 is just 16 times 16, but that's what? 2 to the 4th times 2 to the 4th, which is 2 to the 8th. So we talked about that when we did the last problem. So this, I thought how interesting, the question of the student mimicked what I had already done. So I thought that was a sign to do this problem. So we have 2 to the 8th. And now, of course, we have negative 1. And then, of course, 50 is 2 times 25. So you can see the reason to want to write this as a multiple of 25. And of course, this is going to open the door to nice, perfect cube. So we have the 25s absorbing. Well, that, not there. But this is going to tie in with this. So these will just come together. So this will give us, we've got a negative 125. And then, of course, we have a 2 to the 8th times 2 to the 1st, which is 2 to the 9th. But now we can write these as cubes, and then we're good to go. So now we see what they've got, and we'll throw in the negative at the end. This is 5 cubed. 25 times 5 is 125, which is 5 cubed. And then, of course, this will be 2 to the 3rd raised to the 3rd power, using the laws of exponents. Okay, so now we're good to go. We've got the 8 here, and we've got the 5. So this is negative 5 over 8 cubed. This would make a great test question, basically because it just uses the exact computation, which I've been teaching you all term. The interesting thing here is that, like I've said before, the purpose is to to allow you to work problems in a very efficient manner, knowing that there is a solution. I don't like to give you problems when there's no solution. I mean, it's fine to know when there isn't one. I mean, but at least there's something that is of content. So if you can basically just work the numbers as we've been doing all term, we can see now that r cubed equals the cube of a number. And so we can just take cube roots. So that worked out nicely. I thought it was interesting when I saw the problem with those numbers. I said, these are good numbers. So r is now, by taking cube roots, -5/8. So when you look at this example, what you're seeing now is that this opens the door to solving for A. We've got R, and then we're done. We'll have the first, and then we can solve for the second, and we're good to go. So now let's just use the first equation. So we have what? -50 equals A times R squared. And this is your choice. I'm just going to be lazy. That's too much work over there. This is much easier. So, of course. And so now when we look at this, we have -50 equals A times, of course, this will be what, a 25 over a 64, the negative absorbing in 25 over 64. So if and only if A equals -50, so let's invert 64 over 25. So again, the numbers are nice as we expect. And of course, the 25 will absorb into the 50. So that gives us a -2 times a 64, which gives us a -128. So the first term we have. So this equals first term. Now remember, this is convention. We call the first term A in the geometric and arithmetic. We don't usually call it A1. That way our formulas don't have a bunch of subscripts in them. So first term, technically that's A1, but we use the A, and it really turns out to be a much more computing relevant for computing, so we don't have a bunch of subscripts hanging out. Subscripts are fine, ladies and gentlemen, but I really think some of these conventions were actually introduced to make life easier for us. So now we've got this, and so if you like, we can say the second term, just technically, will just be what? A times R. So now we've got what? -128. And then we have -5 over 8. Here we go again, powers of 2. So now, of course, if we go over here, this is just, if we look at this particular one, 256, so this is 2 to the 7th, right? So this will be -2. Well, the negatives absorb, so just forget that. Don't need to put that in there. So this is 2 to the 7th, 2 to the 3rd, times 5. So this will be 2 to the 4th times 5. So that's 16 times 5. So that'll be a 30, carry your 3, that'll be 80. So this problem really was just number theory, working with numbers. But that's what sequences are. I keep telling my Calculus 2 students, I said, what do we keep doing? Arithmetic. That's all calculus is. It's funny how students will think calculus is just this magical potion that you just dust on a problem and boom. No, it's just arithmetic. Leibniz and Newton figured this out. It's just arithmetic. And that's really why all of our fancy technology works. Without the calculus, we wouldn't have the ability to compute. Students want to do artificial intelligence. They want to work with computers, but it's the mathematics that drives everything. The mathematics drives everything. And so the more you're in love with STEM, that requires that you have a passion for the mathematics. And without it, there is no way no way that you can get where you want to go. Now, I will say this. I have had students in the past that had an intuition for engineering that was miraculous, but they were smart. They said, Professor Ron, I don't love math. I can take this engine apart, put it back together. It's all up here. It's just intuitive. I said, good. But they said, I'm going to do enough work so I can pass. I said, well, I want you to do more than pass. But the key is that they were smart. They were intuitive and said, I'll do enough work. I'm not going to ever love this, but I love engineering. And I said, fine, fine. Get the math foundation that you need to move forward. And that worked perfectly for them. Well, this particular student now is a nuclear engineer. And I thought, yeah, they'll probably end up in mechanical, but nuclear. The student went to A&M and just thought the nuclear engineering department was the best thing since sliced bread. So I said, fine. And so then, of course, I've sent other students there and he'd show them around. And of course, it was biased for nuclear engineering. So now I've got another student who's presently a nuclear engineer. So it's interesting. It's interesting the affiliations that you make as you go through life, and that is the door that opens to something that you end up just having the best time doing. So you never know when that moment's going to occur. Some of you are still trying to make those decisions about your careers, but that's okay. The time will come and boom, the light bulb will come on and you'll be like, I'm done. Okay, so what I wanted to do, since the very last thing that we did before the test or the types of problems that we're going to be doing, we've got conic sections. And so there was another question about a problem in the 11.4 that I thought was good. And so I want to work that. So this will be good. All of this is good review, but this is definitely a good review for the test. So basically, as you study for the test, you've got your formula cards, basically having all of your identities available to you so that you can easily access them. The types of problems, again, with the law of sines, law of cosines, you're very good at that. That you've impressed me with your ability to do that. And of course, if you need an approximation, use your Google calculator. Otherwise, just do everything exactly. And it all involves what? The identities. Use the identities to solve the equations. And then the conic sections are like, you know, algebra, college algebra all over again. So in this particular example, we had two foci. So again, the first focus, and whatever labeling you want to use is fine. So I think this is kind of backwards the way I did it. I usually use the subscript for the larger values, but it doesn't matter. So we have F1 is -1, 2, and F2 is 7, 2. And this is for a hyperbola. The hyperbola. So now you can see that the y coordinate is fixed, and so the motion is along the horizontal direction. So now you can see the transverse axis is horizontal. So this automatically implies that transverse axis is horizontal. So that's good. So that means that the squared term will be the x and the negative will be in front of the y, which we showed when we derived these equations. So, and that of course, we need an extra. And then we had the point 6, 2 is an element of the curve. So, and the question is, write equation of hyperbola. So we know the relationships that exist. We know how to complete the square if we're given a general equation, which is fine, and we know how the A, the B, and the C are related. So the first thing that we want to notice here is that we're thinking, yeah, this is going to help us get A's and B's. But the foci are going to help us out with the C's and the H and the K, the center, because this is translated clearly. Obviously, it's translated. We don't have any zeros hanging out. So that tells you that we have translation of axes, which I spent maybe too much time on. So now recall, we have x prime equals x minus h, y prime equals y minus k. And then, of course, what we see here is that these are the coordinates in the old system. So remember, we just rearranged these by adding h and k to both sides. So x equals h plus, and here, let me write it this way. Let me do this second. That looks kind of awkward. Do the x prime plus h. I think that's how I wrote it. That looks a little better. And then y equals y prime plus k. So now we can use these equations to figure out what's going on. So notice here, we've got the 7 comma 2, and we've got the -1, 2. Now remember, the equations look like this. For the foci, where we have the transverse axis horizontal, remember, this gives us h plus or minus c, comma k. Again, the motion is in the horizontal axis because, again, the transverse axis is horizontal based upon the configuration of the foci. And so now we can use these numbers to figure out. Now notice here, we see that k is equal to 2. The first thing we have is, and this is easy, k equals 2. That's clear from our translation equations right here. And then what do we have? We have h plus c, in this case will be the 7, because c by definition is positive, and h minus c equals -1. So you're thinking, oh, here we're back to college algebra matrices. Well, this is easy. So again, translation equations give us these new coordinates in the old system, and we can use them. So again, k is clearly 2, and now we've got these equations. So we'll add them. So we have 2h equals 6, h equals 3. And then, of course, equivalently, we can use this one because we're lazy. So c equals 7 minus h equals 7 minus 3 equals 4. So c equals 4. So the key here is that with the translation equations, you can get everything you need. And again, they're simple. The rotation of axes is much more complicated. The form of the equations has sines and cosines. They still have these basic shapes to them, but just more complicated, because when you start rotating things, there's just more complication involved. And so if we have some time to look into that, we will. But I'll just have to see how things work out. So now when we look at this, we're thinking, what is our equation going to look like when the transverse axis is horizontal? Well, we know that. We know we have what? X minus h quantity squared divided by a squared minus y minus k quantity squared divided by b squared equals 1. That's our standard equation. And then, of course, how are the a and the c related? Well, that's easy. Now we know that c squared equals a squared plus b squared. If and only if b squared is equal to c squared minus a squared. Okay? So all of this were basically the fallout of all of the analysis we did by interjecting the conventions, placing the foci, c plus or minus c, and then figuring out where a would be relative to c, because the positive constant was 2a. So with all of that convention, this is what falls out. And it actually turns out to be very useful. Now notice, we know what C is. So now we're just going to have an equation in terms of A, which will make this easy because we have a point on the curve. So equivalently, this is an excellent problem. B squared is just C squared, which is 16 minus A squared. That's it. So that's why I do the derivations. That's why I talk about this stuff, because this would make absolutely no sense. And ladies and gentlemen, it is impossible to create new mathematics when you don't understand what you're presently working with. The idea, a lot of you all are going to come up with all kinds of models in your STEM careers, but I want you to know the math so that you can work the math too. And you don't have to go find someone to help you figure out all the mathematics. You should be able to do that yourself. You will have the training. And then you can share, then you can ask your colleagues to say, can you help me refine this kind of thing? And then they say, well, let's work together, and then we'll win the STEM prize, or maybe we'll be Nobel Prize winners. Who knows? Who knows? There are going to be all kinds of prizes awarded with the technology that's coming up, and with the grid. And a lot of you all will stay in Texas and work on that. So there's plenty of beautiful mathematics to be done. So now, if we take this with this and this, we're good to go. So equivalently, so let's write our point. We've got 6, 2 on the curve. So we have, in this case, 6, and I'll go ahead and write H. H is 3. All these numbers we've computed, K equals 2. So we have 6 minus 3 squared over A squared minus, and now we have Y, which is 2. Oh, how nice, 0. So that's 2 minus 2. And B squared is 16 minus A squared, which that'll just go away. So how nice of that, equals 1. So again, when you start this problem, if you think about the translation equations in the general form, then you can fill everything in that you need. And now, of course, this term just zeroes out. So we have 3 squared, that's 9, over A squared equals 1. Well, don't we wish every problem was that easy? So if we cross multiply or invert, we get A squared equals 9. And so this will imply that B squared is 16 minus 9, which is 7. Okay, so again, that not a perfect square, but we don't care. So what's nice about this problem is that if you can do this problem, there's not a single problem you can't do. Okay, it's amazing, and we'll go ahead and do some more stuff here just to kind of finish it off, just to get all the goodness out of this problem. But what we see here is that now we can easily write the equation. So this implies that our standard equation will be x minus 3 quantity squared over A squared, which is 9, minus Y minus K, which is 2 quantity squared, over B squared, which is 7, equals 1. Okay, so again, I thought this was an excellent example because it showcases all of the ideas that we've talked about. Again, I think you're going to find the parabolas and the hyperbolas keep you the busiest. The ellipses are just simpler. Just remember, and I've talked with students about this, the ellipse has the major and minor axis. It's the only one that has that. Okay, the parabola has the directrix, the hyperbola, the transverse. So if you've got those boxes on a hyperbola, that's where they tell you to write DNE, does not exist. So don't fall into that pit by trying to throw conventional terminology onto a conic section where it doesn't exist. That's easy to do. And again, remember, major, minor, that just applies to the ellipse, and that's it. So I like it when a student will send a WebAssembly message and all it takes is 2 seconds and then they feel like, oh, I'm a genius. I said, yeah, you did the problem correctly. It's just a matter of not forcing terminology where it doesn't make any sense. Now, notice here in this particular case, since we've got the transverse axis horizontal, we now know the form of the asymptote. So let's just go ahead and review that. For the asymptotes, and we'll fill everything in, we have y minus k equals plus or minus b over a x minus h. So these are going to be kind of ugly. Sorry, but I just wanted to go ahead and write them down in generality. So now if and only if we have y minus 2, again, use the translation equations here, translation equations equals that we have plus or minus. So of course, b is square root 7, not very beautiful, but we're fine. And then of course, a here, remember that a squared is 9. And so in this particular case, if we look at this, well, I'll find it right here. This implies, let me just go ahead and write these out to the side. A equals 3 by definition. B equals square root 7. So we have 3 here. And then we have x minus h, which is 3. So this will give us y equals, so we'll do the square root 7 over 3 times x minus 3 plus 2. And then we have y equals square root 7 over 3 with the negative x minus 3 plus 2. So that would give you the equations of the asymptotes. So again, just remember the best way to kind of set yourself up for success on the test is to have, again, in the face-to-face test, it would be 10 times more difficult because at home, you've got your formula cards and things. And sometimes in a face-to-face class, I will put formulas on the board and all, but you can set up your formulas and your cards and all that so that you've got access to everything and easily referencing. Okay, so look at this as a big plus. I think some of you are going to miss the online on a schedule more than you might think. It really does provide you with plenty of resources. And so again, make sure before you start your test that you got your formulas and everything set up the way you need it so you can easily access them. I'm trying to lower your stress. I don't want you to think that you need to memorize everything. That's certainly not the case. I'm not requiring that. And like I say, in the face-to-face setting, if I don't have a formula sheet, I put the pertinent formulas on the board, which I don't really expect students to always commit to memory. You'll be surprised, however, how many formulas you actually do know because you've used them a lot. So this, again, kind of gives you the blueprint for working with the conic sections. Just remember the nuances between the two. With the parabolas, you've got the directrix, okay, but everything has a focus, right? The parabola has one, the ellipse and the hyperbolas both have two, and the vertices, which again, when you draw your boxes or you make your little oval or whatever, those are trivial. So again, this is a nice problem to review to kind of put everything into perspective. And I appreciate the question from the student who asked about this. So now what I want to do, I had a student, we had an old test on the test for practice. He said, well, Professor Ron, you have the solutions, but you didn't put up any questions. And I said, well, I thought I pretty much wrote the question hypothesis when I did the solution. So what I did is I just wrote out the actual problems for the student, and I posted those so you may see those. But really what happened is that I had the solutions to all of these, and I just wrote them down longhand and put them on Blackboard. So I want to do several of these. Now, when it comes to the test, again, you'll have your law of cosines, your law of sines. I'll tell you right now, I'm not going to test you on the test with the ambiguous case. that I think you understand. You know, when you have the possibility of the two triangles, that's fine. But again, that's kind of long-winded, and I don't have an issue with that. But I will kind of go ahead and give you the hint that the solutions you'll have will just generate one triangle, and there will be a triangle. So that way you don't have to worry about a long-winded problem that seems to never end. And of course, again, um, being familiar with how you solve sign equations is the most important thing. And you saw how that helps you when you solve trig equations. So I wanted to do just a couple of simplifying examples. Here was one from the test. Here's an example that just said simplify. And in this particular case, we had 1 divided by 1 minus sine theta plus 1 divided by 1 plus sine theta. So of course, this is what you do when you're working with identities. And so if there's some algebraic simplifications or factorizations, you'll need to know that for the test. So in this case, we can just get a common denominator here. Again, we want to combine and reduce as much as possible. So simplification, you know, of course, a lot of you saw with the identities that you really did have to follow what they asked you to do. And if you rewrote the expression outside of what the directions said, you got it wrong. And I'm like I say, that's training. That's training. And I'm, you know, that's what you have to do. And unfortunately, sometimes you have to say, okay, it told me to use the reciprocal identity, and then I just decided to rewrite it in terms of sine and cosine. That was not what the instructions were. So I got that from several of you, but you live and learn. So now we can get a common denominator of 1 minus sine theta times 1 plus sine theta. And so this will give us 1 plus sine theta. And then, of course, plus 1 minus sine theta. Just simple algebra, common denominator. Now, of course, if we look in the numerator, we see that the signs absorb, and we're left with a 2, 1 plus 1. And then, of course, downstairs, we have 1 minus sine squared. Again, the outer and inner absorb, that's just a difference of 2 squares, obviously. And so we get 2 over, in this case, cosine squared, which can be written without a denominator, if you like, of 2 secant squared. So again, when it comes to simplifying, if you're solving an equation, you make things as simple as you can. And you're in control there. Okay, you're in control there. And that's what I'm trying to emphasize when it comes to solving equations and like working with problems. You have complete control. Okay, and that's where your test work allows you to shine. Ladies and gentlemen, if you take the time to write out your work, then you can shine. Okay, but you've got to have some focus. So if you put in the time preparing for this test, it will be very obvious on your test. And that's just the nature of math, is it not? Lo and behold, we are stuck with the arduous task of studying for math. Now, here's another example from this practice test that I thought was good. We're given sine of theta equals 3/4. And we're given that theta terminates in the first quadrant. Well, how nice. I mean, of course, if we have this, we know that we have to be at least in the first or the second. Otherwise, this would be inconsistent, clearly, from our knowledge of the sine function. And what we want to do is compute several things. So first, I'll just say that we want to compute, I'll just go ahead and write this down, sine of 2 theta. Okay, so when this is when you say, oh, Professor Ron, let me check my trig identity chart. Oh, but I know this one, we've used it so much. So you say, okay, this is 2 sine theta cosine theta. So when you look at this, you're thinking, okay, I'm good to go. I've got the sine, but I don't have the cosine. And I know that the cosine is going to be positive because theta terminates in the first quadrant. So we just need a little sidebar. So sidebar, you can do all of the calculation within this, but don't do it. Just go back to it. So sidebar, we can say cosine squared theta will just be 1 minus sine squared, our fundamental identity. So this will be 1 minus 3/4 squared. After all that number theory we've done, this is really simple. We'll take it 9 over 16. So we get 16 minus 9 over 16, which is 7 over 16. So now, in this case, because of this, we select the positive square root. Now, one thing I noticed when I was looking at this particular problem, and I think this is what the student was saying, they kind of thought when I wrote this that they meant that, you know, I meant for them to do this kind of problem. So if you all have worked through this and you were a little bit puzzled about the actual questions, then now they're posted so you can be illuminated there. So now we select the positive square root, which implies that cosine theta will be the square root of 7 over 4. That is square root of 7 divided by square root of 16. That gives us root 7 over 4. So now we can go back to the proper problem and just fill everything in. So we have 2 times 3/4 times the square root of 7 over 4. And of course here, one of the 2 will absorb into the 4. So that gives us 3/2 times the square root of 7 over 4. And then, of course, we can multiply the 2 and the 4. So 3 root 7 over 8. So these, you've seen a lot of problems like this on the test. And just remember, I can't test you on every type of problem, but you know the types of problems that I think are important. If you can do all the WebAssign problems, you are good to go. You're good to go, and even more than good to go. Now, another one that I asked you to do was B cosine 2 theta. Now, when you think about this, and this is always a strategy available to you. Okay, let me just make this comment because you can do these problems many different ways. When you're working, like students would ask about tangent of the half angle. If you knew cosine half angle and sine half angle, well, then you can just take ratios to get tangent. You're thinking, oh, but you have that remarkable formula. Right, but you know, if I can take the ratio of 2 numbers to get the tangent, then I'm done. So you don't have to follow every strict new identity. If there's another way, just using the fundamental constructs. So when you're working these problems, I'm not going to be bothered at all by how you do it as long as you use legitimate mathematics, which is fine. I don't want you to say, write this down and say this equals this, and you leave out all of this. Of course, there's no credit there. If you used a fancy calculator, then you know, sorry, okay, that is not showing me that you understand anything, okay? I can teach a 5th grader to punch buttons in a calculator, ladies and gentlemen. So don't do that. But if you get to this problem and you say, oh, Professor Ron, I just computed this. Can I work the fundamental identity here? And then you have to think, okay, if I do that, then, and let me give you this idea. If I do that, then I've got to negotiate this. Where does 2 theta live? Okay, so the idea is that we would know that would live in the 2nd quadrant, okay? We know that, but if you don't want to have to do that analysis and then you're thinking, oh, I'm not sure, then you can go directly to the identity form of this to relieve you of all of that. So you have flexibility, but you have to keep in mind that you may have to choose a sign. And if you have to choose a sign, you're thinking, I don't want to do that. So In this case, what I would recommend is just going to the form that's really simple. Remember when we did the subtraction formulas and the addition formulas, we had something like this, okay? And then what we wanted to do was we would replace cosine squared with 1 minus sine squared. This is what we did, the same old song and dance with the power reducing. So you already know this. So if you look at this, you're thinking, okay, I can go ahead and use this formula and just use this and be good to go and not have to worry about doing anything fancy, okay? So in this case, we have 1 minus 2, and we have sine theta squared, so we've got 3/4. So this is the road of least resistance, so to speak. So this will be 1 minus, and now of course we can square this out, and I know I'm doing extra work. This is, let me write this out. We'll just do it the straightforward way. So we have 2, and I don't need the times here, times 9/16. Now, of course, the 2 will absorb into the 16, so that gives us 1/9/8. And so now we have 8 minus 9/8, and this gives us a -1/8. So when you do these types of problems, choose the route that's easiest. And if you find another route that doesn't force you to pick signs or whatever, then that's probably the better way to do it. And of course, this just requires that you have a nice listing of your identities or you remember this from lecture, okay? So you have flexibility. Just remember that you want to make sure that if you choose an alternate path, that you don't miss something, okay? So now let's look at a couple more. These are kind of fun. Not difficult, but kind of fun arithmetically. The other question here, let's see, what did I have? I said sine of a half angle. So let's compute this, sine of theta over 2. Now remember, let's just go ahead and write down what this was. This was plus or minus. In this case, we have 1 minus cosine theta divided by 2 to the 1/2. Now, this again is all related to the power reducing formulas that we used. And so now we have to look at this and say, okay, well, this is where we can use that theta terminates. Let me go back to the original. Theta terminates in the first quadrant. So theta is here. This implies that theta over 2 is also in the first quadrant, okay? So now, if this is true, we know that sine of theta over 2 is also positive, so this means select the positive. So this will say select positive radical, just like we've been doing before. So that's important. So now, if you like, we'll have sine of theta over 2 equals the positive radical. So I won't put anything here. Now, notice we don't have cosine, so let's go ahead and figure that out. Notice here, if we look, well, we did, boom, right there, we do have it, sorry. We do have cosine, it's right there. So now we'll use it. So take this and substitute. So now we've got the cosine here. So we have 1 minus square root 7 over 4 divided by 2, 1/2. So now when you look at this and you think about what we're doing, it's like, okay, looking at what we have and thinking about this in terms of what we've already done, again, we write the formula, we make the selection of the radical, we go back and look, have we already computed this? We had. We substitute, and now we just make it look a little bit more user-friendly. So let's just go ahead and get a common denominator. So we have 4 minus root 7, and then 4 times 2, that'll give us an 8 to the 1/2. And so if you like, you can, this is fine. If it's not one of the answers, you could, adjust it a little bit. So we have the square root of 4 minus square root 7 divided by the square root of 8. Remember, that's just 2 times 4. So this could be written as 4 minus the square root of 7 square root divided by what? 2 root 2. Now, of course, you could rationalize that if you want. So this is where you think, okay, not a beautiful number, but certainly a correct number. Now, at this point, the very last problem, so I thought this was a good example. We have sine of, cosine of theta over 2. We just did that one. I printed all this out, but boy, when I print out something that's printed, it gives me a color of ink that's hard to read. So now you're thinking, okay, we can be lazy, and I'm going to be lazy. Reason being is that when you think about this, we could square this and subtract from 1, but that's a big old mess. So we're just going to use this formula here and select the positive radical. So now again, we have plus or minus. So this is the road of least resistance. 1 plus cosine theta divided by 2 to the 1/2. And again, with this analysis that we have here, we select positive radical. So that makes our life a lot easier. And then now the only difference here, ladies and gentlemen, is the plus here. Everything else is the same. So this will be, we'll just fill it in and jump to the punchline. So we have 1 plus square root 7 over 4. And this is so much easier. So this is the path of least resistance. So we can just jump to this. So ... square root 4 plus square root 7, or the square root of 4 plus square root 7 divided by 2 root 2. So when you look at this, depending on what you have to do, think about what you have with your identities and think about how much simpler this is. Now, like I've said before, you have plenty of flexibility, but if you're working a test, this is certainly a quicker way to do it. And you can always look at your formulas and make that deduction as you're working. And again, the result is what you need. And of course, since you get to select results, you can always kind of look as you've done your work and say, okay, this is the result here. Just avoid trying to work backwards because that gets you nowhere. And that's so obvious when you've done it. And it's not going to get you any credit. Now, so some other examples that I've gotten questions about. Let's see, there was one, oh yeah, power reducing. You all are pretty good at this, but there was a power reducing question. And then there was a question about solving an equation. So this is an example that comes up a lot, but here's one. So for instance, we have sine to the 4th. I'll just use an X now because you use that a lot in calculus. And in this case, we want to write as first powers of cosine. Now I think during office hours, I did like a cosine to the 6 and a sine to the 6, and then there was a cosine squared times a sine to the 4th, the same kind of thing. But this is a technique that you'll use in calculus, and it basically is a springboard from the last problem we did. So we know the power reducing, and this is a very, very, very nice example that is very powerful in the calculus. That is sine squared of x is 1 minus cosine of the double angle. So I'm using x instead of theta this time, so it'll be easier to write. So this is the power reducing. That double angle formula for cosine is really a nice result. They give us the half angle formula for tangent and all of that. And of course, ladies and gentlemen, you don't use all of these identities a lot. Some you don't use except sparingly. So you always need to have them in your back pocket easily to reference. So now, of course, this is a nice simplification, which now will introduce a first power of cosine. So now we can go ahead and write that. So we know this is sine squared x quantity squared, right? So we can take the sine squared and replace it with the power reducing. So this will be 1 minus cosine 2x over 2 quantity squared. Now, since we're lazy, we just get a 1/4 downstairs, so we'll bring that out to the side because we don't want to worry about it anymore. And then we have to square the numerator, so that'll be a 1 minus a 2 cosine 2x. So now we see both of these are fine. There's a first power of cosine, but now we have plus here, so plus cosine squared 2x. So when we look at this, we're thinking, okay, these two are good to go. Check and check. But this is a square. It's not a first power of cosine. We don't care about the argument. We just want the power of the cosine to be 1. So now we apply the double angle, but now this is for cosine. Will be 1 plus cosine 2x over 2, just like the half angle formulas. So this will give us 1/4, 1 minus 2 cosine 2x. And now we'll apply this. So this will be, and we'll just pull off the 1/2 to the side, plus 1/2. And so we have 1 plus cosine of the double angle. So the 2x becomes 4x. And now, of course, the old trick here is to say, we don't want to have to navigate all of these 1/2s. So we can just factor the 1/2 and hit these with a 2 and just bring this outside to give us a 1/8. So factor the 1/2. So that'll give us a 1/8. And then pay for it here, 2 minus 4 cosine 2x plus 1 plus cosine 4x. And now, of course, we can combine a couple of terms and we're done. So we get 1/8. So we have 2 plus a 1, which is a 3, minus 4 cosine 2x plus cosine 4x. Now, like I say, there'll be examples with the triangles, the law of cosines, law of sines. Again, you're good with those. There'll be equations to solve, simplifications, conic sections. Again, just all the standard type of questions. But this is good to know just because this is a technique that you will use when you do the reduction formulas for integration by parts, and also when you do trig integrals. And I think a lot of you will enjoy using these. And like I said before, these are integrals that you can quickly do from your techniques that you learn in Calculus 1. So the key here is to use the power reducing to work with these even powers of sine and cosine, which again are somewhat of a nuisance without these identities. So that's a nice example. Now let's look at an equation. So some of these, I think you can solve all equations, for all solutions, but that just means that you exhaust 0 to 2 pi, and then you can extend, especially when you're working with sines and cosines. So if you can master the 0 to 2 pi, then you're in good shape. So here's an example. Let's look at this one. So I'll say solve, just as a nice review, solve in 0 to 2 pi. And we have 2 sine squared theta plus sine theta minus 1. And you know, I'm a big fan of the lemma, the a sine x plus b cosine x. You know, that you should know that's always useful when you're solving equations. Yeah, just recall, I've spent quite a bit of time on this. This should be on your note card, a sine x, where the phi and the a comma b terminate in the same quadrant. This is a good thing to know. B, I've done many examples with this. Cosine bx is the square root a squared plus b squared sine of x plus phi. Again, AB and phi terminate in same quadrant. You got to have that. Otherwise, you just write down nonsense. Quadrant. And of course, tangent of phi, that's how you select the phi, is b over a. So go back and look through that. That's a really important construct, and it gives us power with solving equations that we really do like without having to square things. But again, this turned out to be interesting, and as you work through in your mathematics classes, you'll have more opportunities to use this. Now, of course, when we look at this, we breathe a sigh of relief, basically because we have one sine function and we can see that it factors. Because if you look at AC, you have what, 2 times a negative 1. And so when you look at that, you say 2 plus negative 1 is what? 1. So that's a check. So this if and only if, so didn't have to work very hard for that, did we? So we have 2 sine squared theta plus 2 sine theta minus sine theta minus 1. I thought I'd just work it out like we did at the very first week, just to remind you of where we've been. And then, of course, factor by grouping. So we'll have, in this case, 2 sine theta. And in this case, if you look here, this will give us a sine theta plus a 1. And then, of course, here we can factor the negative, plus negative 1 sine theta plus 1. So this is a blast from the past. So when we look at this, again, we've got zero product. So now sine theta plus 1 times, in this case, if you want, I'll go ahead and factor this again. We've got what? 2 sine theta minus 1 equals 0. So 2 sine theta minus 1. Again, when you check this, we get the square, we get the negative 1, and we get the in this case, the 1 here, the 2 minus the 1. So this all checks out. Now, of course, here, since this 2 is kind of in the way, we'll go ahead and factor this. So we get 2 sine theta plus 1 times sine theta minus 1/2. And so now these are all good to go. So by zero product rule, we have sine theta equals negative 1. So that's on the axis. So we love these. These are like easy as pie. Or sine theta equals 1/2. So again, these are when we have ones like this, we just say, well, that's easy. There's only one case where this is actually true in 0 to 2 pi, and that's at 3 pi over 2. We know that the sine is 0 on the x-axis. It's 1 at the positive y-axis, and the negative, that is in the lower quadrant, gives us the value 3 pi over 2. So there's only one here, theta equal 3 pi over 2. And of course, we wanted to extend this to all solutions, we just add multiples of 2 pi. So that would be an easy extension. So that's quick right there. Now here, of course, we have theta equals the inverse sine of 1/2, which is pi over 6. And of course, this is a solution in the first quadrant. So the second solution by Professor Ron's lemma is this solution subtracted from pi. So we'll say second solution. You can give it another letter if you want. You can just call it alpha or just write second solution. It doesn't matter. Pi minus pi over 6, which is 5 pi over 6, which is here. So now we combine everything and we're done, Professor Ron's lemma. So now we can list them. We have what? Pi over 6, 5 pi over 6, and 3 pi over 2. This was asked about, let's see, there was another one. There was another one somewhere that I think, yeah, that covers it. There again, I think there was a situation here where they thought this was a simplification, and so maybe it's good that I actually wrote out this. And so when I put the test questions up, I just said solve in 0 to 2 pi and wrote it this way, so it was clear. So I saw that there was a little misunderstanding about that. Now, one thing that is good, since I've mentioned this, is to deal with multiple angles. So let's look at one of those. So here's an example. So say we had something that looked like this. So we had cosine, well, let me write it this way, and I'll do it user friendly. Oh, I'll do a cosine. In this case of 3x, and I'll have a 2 here. We'll do plus 1 equals 0. And I'll say solve in 0 to 2 pi. So I'm trying to look at some basic constructs, because if you can do these, you can do anything. This last example, you'd be surprised how this is missed completely. Again, the basics are what are important, because as we do the fancier ones, as we've done in lecture, they all revolve around this. It's the same technique over and over. So when we look at this, we're thinking, okay, well, this is like what we had before, but less work involved. So the first thing we're going to do is divide by 2. So equivalently, we have cosine of 3x plus 1/2 equals 0. So now we're good to go. This is like zero product, but now we've got the multiple angles. So I think this is important. So equivalently, 3x, well, let me not skip this step. Shame on me. So cosine of 3x equals negative 1/2. Then equivalently, 3x equals the inverse cosine of negative 1/2. Now, the reason I like to do these is that we spent ages on inverse cosines or inverse trig functions. Remember, the inverse cosine, I'll just use another variable theta, lives between 0 and pi. So you can use the formula that deals with the inverse cosine of the negative angle, or just remember that. So let's just say that we want to dispose of this. So this is going to be pi minus the inverse cosine of 1/2. That was an identity from chapter 5. So this will be pi. Now, when we think about this, we're doing the inverse cosine of 1/2. Now, again, this is in the first quadrant, and that's going to give us what? Pi over 3. So this is in the first quadrant, element 1. So this gives us 2 pi over 3. So now what we can see is, again, we've got another nice identity, inverse cosine of negative theta is pi minus inverse cosine of theta. That's very useful. Deal with the negatives or just use the unit circle directly. Remember, this is important. This is how we've defined things. So now, here's our first set. Then we're going to use Professor Ron's lemma. So this implies if and only if. Now, we don't have to extend. We want to extend because we want to make sure that we get all copies. So let's extend and then check out to see if we get some additional solutions. So this will say 3x, let's do the extension, 2 pi over 3 plus 2 pi k, okay? Or now by Professor Ron's lemma, we'll have 3x. And notice by Professor Ron's lemma, the second solution will be 2 pi minus 2 pi over 3. So that's going to be what? A 6 pi over 3. So this gives us 4 pi over 3. That's the second solution by Professor Ron's lemma. So now we have or 4 pi over 3 plus 2 pi k. So when you think about this, this is exactly what we do. Even if we have more algebra to do, we still end up doing the same thing where we exhaust 0 to 2 pi. So if you can master 0 to 2 pi, then there is not an equation that you can't solve. And I'm not going to give you anything on the test, or I haven't given you anything on the test that you can't do by the means that we have discussed. Again, when you get to calculus and you learn Newton's method and you need some approximation techniques, then that'll make perfect sense. Okay, and then you'll have this nice second order method to utilize. And when it's funny, when I taught the open books class and I used the Schaum's outline, this book, the Schaum is the classic book, and they had some great problems on Newton. And the students didn't like it. They're like, "We're done with this, Professor Ron. We don't want to do this anymore." I said, "But this is crunching numbers, and this is what you live for." So just remember, all the problems on the test will be things that you can solve. I just keep this Schaum outline right by my desk where I teach, and like I say, these are the new ones. Back in the dark ages when I was an undergraduate, they weren't nearly as nice and beautiful. They were pretty shabby looking, but they still had good content. So now x will be 2 pi, divide by 3, that'll give us a 9, plus 2 pi k over 3. Now, if you like, we'll do the same thing here. So we have x equals 4 pi over 9 plus 2 pi over 3k. And let's just get common denominators. So we have 2 pi 9 plus, so we'll do a 9, so 3, so that'll be a 6 pi k. And then 4 pi 9, same thing, plus 6 pi k over 9. So now let's just start listing some values. So we'll take k equals 0, so we get 2 pi over 9. So this is k equals 0. Again, notice we put everything where we need to have it, in 0 to 2 pi. And these are the first ones that we get. Now we can let k equal 1. So this will be 2 pi over 9 plus 6 pi over 9, which is, in this case, 7 pi over 9. So this is k equals 1. And now if we go to 2, notice we're going to get a 12, and we're still good, k equals 2. So we have 2 pi over 9 plus 12 pi over 9. And that gives us what? 14 pi over 9. And then if we do k equal 3, in this case, we'll have an 18 here and plus a 2, that'll give us a 20. So that'll be too big. So here is too big. Okay, so we'll go past 2 pi and then we'll just back around to here. Okay, so now that's for the first part. Let's look at these. And so let's put boxes around the ones that we know are good. And let's look at this side. So we'll have k equals 0, 4 pi over 9. Again, all mutually incongruent. K equals 0. And then we have k equals 1. So again, we'll have 4 pi over 9 plus 6 pi over 9. That gives us 10 pi over 9. That's good. That's less than 2 pi. And then we have k equals 2. So we have 4 pi over 9 plus, now we get the 12 pi over 9. And that gives us 16 pi over 9. Now, of course, when we do the 3 again, we get the 18, and the 18 plus the 4, that's giving us the 22, which is bigger. So that just gives us right back to here. So the next one, k equal 3, too big. So now, mutually incongruent. So this is kind of nifty. And this is what you had to do in your WebAssign when you would do your homework. So now when we list everything, we can just start here. So here are the solutions that we're interested in. Solutions in 0 to 2 pi. So this gives us 2 pi over 9. I'll just start here and list. Well, I guess we can do them in order. 4 pi over 9. And then 7 pi over 9, numeric order. And then 10 pi over 9. 14 pi over 9. And then 16 pi over 9. So when you look at this kind of example, I'm sorry, ladies and gentlemen, I get to the bottom of the page. You have to love the new IPEVO software upgrade. It is so nice. Doesn't glitch anymore. I mean, that is amazing. And now when I open it up, it says, do you agree with the terms? You know, like, of course I do. You know, we're going to say no and then I can't use it. But now they're just being very like, okay, we've made some changes. Do you agree with these? I'm like, yes, I agree. It's amazing because I was telling you all last week when it updated, I'm thinking, oh no, they've changed this stuff up, but it's just seamless. I guess they decided, like I said, they got their engineering department, computer engineering department, to kick into high gear, and you got this beautiful screen. And the thing is, and this is what I was saying to some students in the class, that the software is now taking advantage of Professor Ron's good internet connection, Xfinity, you know, you're paying through the roof for good internet connection, and plus the computer I have. If the software does not take advantage of the hardware and the internet connection, it doesn't matter how good you have. You know, that's what everybody's not understanding. And I kept thinking, you know, this IPEVO, occasionally, if I move kind of quickly, it'll glitch and freeze, and then it unfreezes, of course, it's fine. But now they have software that takes advantage of the memory, takes advantage of the internet connection in a beautiful way. And you can see how nice it is. What I had before, I'll take it. It was wonderful. But this is even better. So sorry to digress about that. But as you prepare for the test, again, make sure that you have your identities accessible. You can use the formula charts on Blackboard, or you can make your own. Like I say, I've got students who still have Professor Ron's unit circle with their formulas written on the back. And these are students I had 10 years ago when I first started at the North Campus. I think it's hilarious. And they always said, well, I was looking online to find that unit circle. Where'd you find it? I said, you won't find it. I said, you'll find it, but it's mine. They're thinking, oh, it was something I just, took from another site. I said, no, I coded that in LaTeX. So they still have it with their formulas penciled on the back. Make sure you have those accessible and have a chart that also covers the conic sections. Now, of course, when we do the final, you want to have a chart, with the sequences, geometric, arithmetic, and then, the induction and the binomial theorem that we'll do next week. But make sure you have that accessible, so as you need it, you've got the equations that are pertinent. And just remember, as you write out your mathematics, write with purpose. Think about how I teach you, write with purpose. And as long, ladies and gentlemen, as long as you provide the essential techniques. I know a lot of you, then you jump to your fancy calculator and compute everything. That's fine. As long as I can see the logic, that's what I'm looking for. I still think some of you think I don't even look at the test work. Ladies and gentlemen, I look through every line of your test work. And then I assess how many points you're going to get. Are you going to get all the credit for that problem, or are you going to lose some points? And that's how I come up with partial credit. And in most cases, it will be negative. Okay. So now that you understand that, you know what I'm looking for. An unsupported response is a wrong response. Okay. So I'm not saying this to be the tyrant of mathematics. I'm saying this because as a future STEM professional, you will have to do this. You will be required to substantiate what you do. I mean, let's face it, ladies and gentlemen, in our technological world, you can't do anything and then people are just pick you apart. Oh, well, you didn't do this, you didn't do that. No, with mathematics, you are in complete control. Okay. It's not opinionated. A lot of you think, oh, well, if I don't do the problem the way you do it, you're going to mark it wrong. That could not be farther from the truth. Okay. You know this. If you do your work correctly with mathematical integrity, it's fine. I don't care, but it's got to be your work. The fact that I don't think you're going to come up with a great technique beyond what I do is not anything except you're still growing. Okay. Once you have worked in STEM for 20 or 25 years, then you can write your own textbooks in engineering or whatever. And that's what you're probably going to do, because you're going to get tired of what you're doing and you're going to say, well, I'm going to write some books and illuminate everybody with my great techniques in computer science or computer engineering or biomedical mechanics or something, just all kinds of things. So just remember, the test work you're submitting now is preparing you for greatness. Okay, so let's not complain anymore. Let's work hard and do your best work. That is all I have ever asked of you. And I appreciate the fact that everybody is so much more positive now. I don't get threatening emails anymore or unkind emails. That is truly a blessing. The members of the choir last night, they said, how are things going? I said, my students are figuring out what it means to be a STEM major. And so the choir where I play at First Presbyterian in Pasadena, they pray for you all every week, okay? Because they know that what I'm requiring of you to do is very difficult. I know this. But you are aspiring to greatness. And when you do that, there are dues to be paid. It's like my mom always said, and my grandmother Alice always said, Ron, you work so hard. I said, well, you know what? I'm trying to make a way for myself. And I'm trying to help you make a way for yourself so you can change the world. So I appreciate your attendance today. I wish you well as you prepare. Get some sleep, rest up. When you take your test, be refreshed, have your notes and your formula cards ready to go, and I wish you well. I will send out email invitations for my conference hours today. So if you have additional questions, please stop by or just send me a WebAssign message. I'll be sure to answer it. So everybody take care, and thank you for your attendance today.